Hi guys, so in this video I'd like to speak about a new structure called binary heaps. Now, in the past we spoke about a structure called a priority queue, which was just like a normal queue, except that rather than giving us values back in the order that we put them in, it rather gives us back in the order in descending or ascending order of some extra priority that we add in. So for example, if we have, let's say we have a queue of A, which has a priority of 0, then maybe we have a B with a priority of 4, and we have a C with a priority of 3, and we have some queue where these items are all added in, and then we want to say DQ, give me the next item that has the biggest possible priority in the queue. So in this case we could then search through the queue and we'd be able to see that the largest priority is item B, and so we return that value from the queue, and that would now have these two items left, A and C, sorry. So originally the way we did this was to say either we always insert items in the correct order so that we make sure that the list is sorted, and then if the list is sorted, then it's just a case of finding the item at the front or the back of the queue. The alternative was to say that we could simply remove, we could search through the entire list every time and just remove whatever item has the largest priority. So in the first case where we need to keep the list sorted, if we scan through and say, okay, there's an A with a 0, there's a C with a 3, and let's say we were inserting the B with a 4. In this case, we would scan through and say, okay, well, it's bigger than 0, so we carry on. It's bigger than 3, so we carry on. And so we then insert it at the back over there, and we would say B with 4. In this case, in the case where we're keeping the list sorted, it means that in the worst case, we have to do n comparisons. So in the worst case, we're always inserting at the back. But we only know that once we've already looked at n items. So in the worst case, we're looking at order n for an insert, but then order 1 for removal. So when we fetch a large item. So in that case, we've got potentially slow inserts, but we've got very fast removals, or when we get the largest item from the priority queue. On the other hand, if we just insert items wherever we want, we can always insert at the front of the queue, which would then say take order 1. But then when we're searching through, we then need to visit every single item that's in the queue to make sure we're returning the one that's actually the biggest. So in that case, it takes order n at the end of it to find the maximum number in every queue. Okay, so that gives us two different implementations of a priority queue. There's one thing when you're trying to decide which one of these two implementations you want. If we've said we can insert in linear time or constant time, and then we can pop in constant or linear time, I would be inclined to say use the second approach, unless you know that you have some memory pattern that you can take advantage of the cache. The benefit of the second approach is that you're guaranteed that any item that you remove from the list must already have been inserted. So we know that in order to remove an item, we must have already added it to the list. So we know that we could potentially add n items. But if we don't actually remove all n of those items, then we might only be calling the pop function maybe 5 times or 10 times or some number that's smaller than n. So we may as well say that the operation that we know we'll do more of, at the very least, let's make that one fast, and then the other one where we may do fewer of those, then we can make that one the slower operation. So in this case, I would say rather have your insert function be the constant time one and your remove function be the linear time one. In the case where you do the exact same number of inserts and pops, so pushes and pops, when we add and remove the same number of items, in that case it probably doesn't matter so much, and then you can rather think about how your data structure is built and how it will be accessed and what kind of caching you can use to try and get better results. So we see that if we are building a priority queue using an list or array type data structure, we know that we can then get inserts and removes in constant or in linear time. So we're now going to look at using some kind of tree structure to see if we can speed that up from being linear to something maybe a bit better. So we're going to look at a structure called a binary heap. Now a binary heap allows us to access the maximum number from a collection of numbers in constant time. It allows us to remove it in logarithmic time, and it allows us to add a new one in logarithmic time. So those are my claims, that we can now add and remove items. So we can say maybe push and pop as before, and we're going to say that we can do that in some kind of logarithmic time. Alright, so a binary heap is simply a complete binary tree. So if we remember that a complete binary tree was a tree that was perfect except for possibly the very bottom level, and that bottom level had to fill up from the left-hand side. So this is a complete binary tree, so is this, because this top bit over here is perfect, and the bottom layer we see has 2 nodes in it, but it's filled up from the left-hand side, so there are no holes in it. If we added in a node over here, this would no longer be a complete tree, because we would be missing this node over there. Okay. So if we look at a complete binary tree, we can guarantee that the height of that tree is going to be logarithmic. So we can say that this is a complete binary tree of height 2, and that this complete tree has the smallest number of nodes that it can possibly have for being a complete tree of height 2. On the other hand, we can say we can have a complete binary tree of height 2, and the maximum number of nodes that it can have will be when the bottom level happens to have the maximum number of nodes that it can have. So in this case, we see that it's also height 2. We see that the tree is actually a perfect tree as well. So in class, when we did binary trees, we looked at the number of nodes that we could have, and we said that in a perfect binary tree, we know that the number of nodes in the tree is going to be 2 to the h plus 1 minus 1. So that's the maximum number of nodes that we can have in a perfect binary tree of height h. On the other hand, the minimum number of nodes that we can have in a complete tree of height 2 is simply going to be the number of nodes in the complete tree, which has height equal to 1, plus that extra 1 node that we have. So if we know that the perfect tree has 2 to the h plus 1 minus 1 nodes, and the height of that tree in this case is going to be 1 rather than 2. And in general, the height of that perfect tree is going to be h minus 1. So we can add in the minus 1 over there. So h minus 1 plus 1. And then take that entire thing and add on this extra 1 node there. So we add on that plus 1 there. And so if we look at all the numbers, we can see the plus 1 minus 1 cancel out, and the plus 1 minus 1 cancel out. And we see that the minimum number of nodes that you can have in a complete binary tree of height h is simply going to be 2 to the h. So we can now use this to guarantee the height of our tree. And we can say that if n, the total number of nodes in the tree, that is going to be greater than or equal to 2 to the h. So we're going to say that the number of nodes in the tree has to be either the minimum or it has to be bigger than the minimum. And so this gives us quite a nice inequality here, that we can simply take the log on both sides. So log base 2 of n is going to be greater than or equal to log base 2 of 2 to the h. And we know that using our log laws, we can bring the h out in front. Log base 2 of 2 is simply 1, so that's h. And we've got log n on the other side. So we're saying that h is bounded above by log n. H is less than or equal to log n. So in this case, we know that h is an element of big O log n. So the height of a complete binary tree will always be logarithmic. And so we know that if we have to do some kind of operation that potentially runs the entire height of the tree, we know that the number of steps that we're going to have to do is going to be bounded by some logarithmic number. Now there's another useful property of complete binary trees that we haven't mentioned before, and that's that they can actually be represented really nicely in a normal array. So for example, if I have a complete binary tree that looks like this, because I know that there aren't any holes in this, that there's always going to be one number followed by the next, followed by the next, and the next, and the next, I can represent this using an array. So say we have an array like this, then we can number each of our nodes starting from 0. And we can say, well, the root is going to be index 0. And then from there, we simply number all of our nodes by increasing that index by 1. So, for example, if we add in this extra node, that will be at index 4. The next one would be 5, and the next one 6. And from there, we can then just say these numbers correspond directly to indices inside our actual array. So if we had the value 42 in node number 0, then 42 would go over there. If we had the number 36, it would go over there. If we had the number 30, it would go over there. And we can carry on like that. So it means that for a complete binary tree, we don't need to worry about having nodes with left and right pointers. We don't need to keep track of any of those things. We can simply keep them all in the array. And remember, in the same way that we had this issue with linked lists, we know that an array is going to be faster to access than to use the pointers because we're going to get all the benefits of the cache. So, and that comes from something called locality of reference. And that means that all of the numbers in memory are right next to each other. So when we ask for the root over there, its children and the other numbers next to it are going to get loaded into the cache depending on the size of the cache line. And that will depend on the CPU hardware. But it's important in that we know then that we can access the neighbors or the children quite quickly and easily. So if we're representing a complete binary tree in this way, we can then simply calculate the index of its children and parent very easily. So, for example, if we're at index I, let's say I is equal to 1. So we're somehow at the node with 36 in it. We're at the node that has 36 in it. So I equals 1. We can then say, if we want to get to its left child, we can say, well, the index of its left child is simply going to be 2i. So in this case, it's going to be 1 times 2, which gets us 2, and then we're going to add 1 in order to get to that node. If we were currently at node number 2, we would be saying 2 times 2, which is 4, plus 1 gets us to 5, and that's the exact place where the index for 30's left child would be. On the right-hand side, we can simply say, well, it's going to be the index to the left child plus 1. So the right child will always be the left child plus 1. And so in this case, it's 2i plus 2. And that makes a really easy way for us to get to the children of some node I. On the other hand, if we're trying to get to the parent, then we can simply rearrange these two things. And we can say, okay, well, if we are a left child, then we're looking for I. So in this case, we can say it's going to be the index minus 1, and that's going to be equal to 2i. And so we can divide by 2 on both sides. And that shows us that the parent of a left child is simply its index minus 1 divided by 2. On the right-hand side, we have the exact same thing, except it's going to be r minus 2 instead of r minus 1. Now, if we use integer division, or if we simply round down, then we don't need to deal with two different equations. We can simply take one equation and round down whenever necessary. So now we know how to get from a left child to its parent, and we know how to get from a right child to its parent. If we use integer division, then we can see that this actually works out quite nicely, and we can simply say that the parent of any index is going to be that index minus 1 divided by 2, and we round that number down. And we'll see that by rounding down, it means that this works for both the left and the right children. So it works when the index is odd and when the index is even. So in this case, if we're at index number 3, 3 minus 1 gives us 2. 2 divided by 2 gives us 1. And indeed, that is the correct parent. If we're at index 4, 4 minus 1 is 3. 3 divided by 2 is 1.5. But we're taking the floor of that number, so we're rounding it down, and so that gives us 1 as well. Likewise, if we're at 2, 2 minus 1 is 1. 1 divided by 2 is a half. If we round that down, it takes us to index 0. If we're at index 1, 1 minus 1 is 0. 0 divided by 2 is 0. And that takes us to 0 again. Okay, so you're hopefully comfortable now with how to implement a complete binary tree and how we might be able to implement it using an array, and if we have used an array, how to traverse between different nodes. So if we're at index 1, we can find the index of its left and right child, or we can find the index of its parent if necessary. Now let's have a look at how we can use this to implement something called a binary heap. So a binary heap is just a complete binary tree with some added order condition. Now this order condition is for a binary heap is called the heap condition. And the heap condition tells us that the value of the parent must be greater than or equal to the value of the left child and the value of the right child. So the value of the parent must be greater than or equal to the value of the left child and the right child. So if we have a look at some tree, like this, we see that indeed it is a complete binary tree. And so if we fill in our numbers, we can say 42, 32, 10, 5, and 6. So in this case, we can see firstly, it is a complete binary tree. So this first condition is satisfied. And the second condition, we see, well, 42 has 2 children, and its children have values 10 and 32, and 42 is bigger than both of those. On the left-hand side, we see that 10 has 2 children, and we compare the parent's value to both of the children, and 10 is bigger than both 5 and 6. 32 doesn't have any children, and so the heap condition is fine there. If it did have an extra child like that, then we would just need to make sure that whatever value was stored there was indeed going to be less than the parent. And so one property of this is that any number that's higher up in the tree is going to be bigger than any of its descendants. So 10 is going to be bigger than 5, it's bigger than 6, and any of their children as well, it will be bigger than those. Similarly, 32 is going to be bigger than any of its children, and 42 is going to be bigger than any of its children. And so this automatically means that the largest number floats up to the top of the tree. And so in a max binary heap, or in the kind of binary heap that we're looking at here with this condition, the biggest number is always going to float up to the root of the tree. If we wanted to say find the minimum value every time, then we would change our heap condition to simply say that the value of the parent must be less than or equal to the left and right children. So if we wanted the minimum number every time, then we would use this heap condition on the right. If we wanted the maximum number every time, then we use this heap condition on the left. Now it's important to note that this is a complete binary tree with a heap condition. It is not a binary search tree. So in this case, I happen to have drawn one, but this would also be perfectly valid to say that 6 and 5 go like that. Or even that 32 went on the left and that 10 went on the right, except for the fact that the binary heap condition is now broken here. So in this case, we would need to actually have 24 up here and 10 down here. So as this is also a binary heap. So as long as it is a complete binary tree, so we have some structural property, and that the heap condition is maintained, then numbers can go wherever they fit, as long as the heap condition is maintained. All right. So let's have a look at some other examples. If we said so if we had a tree that looked like this, we can ask ourselves, is this a binary heap? So the first thing we look at, is the structure of the tree, and we can say, well, it's not a complete tree because there's this hole over here. There should be a node over there if it were a complete tree. And so because it's not complete, this is not a binary heap. If I then came in and added in a node, so we said, okay, let's say there's a 5 over there. Now, we can see that this is now a complete binary tree. So it's a perfect tree, and the bottom level has filled up from the left, and there are no holes. So this is a complete binary tree. And then we can go in and look at our heap condition, and we see that 100 is bigger than both 12 and 53. 12 is bigger than both 11 and 5. 53 is bigger than both 25 and 6. So this one is a binary heap now. And so we're happy. Now let's consider the different operations that we need to do. So we said that for a priority queue, we needed to be able to insert a new item. So we're going to say push, and we're going to say pop, where we remove an item. Now, we're using the binary heap to implement the priority queue. And so our binary heap needs to satisfy these two functions. So let's have a look at push first. So how can we add a new item to the tree? Well, because we said that it's a complete binary tree, there's only actually one space on the entire tree where we're actually allowed to add anything in. If we added something in to the right of 6, it would no longer be completed. In fact, any of 6's children, 25 or 5, would mean that it's no longer a complete tree because we would have introduced a hole over here. So for a complete tree, there's only ever one space where we can add in. And so we're simply going to say is, when we get a new item to add in, then we always go to that next open space in the binary tree. And so in this case, let's say we're inserting the number 42. So we go into our complete tree. We say this is the only place we're allowed to insert it, and so we do that, and we insert 42 over there. The next thing we need to check is that we haven't now violated our heap condition. And in the same way that we had an AVL tree where we would do an insertion and then check whether we'd broken the condition, we're going to do the same thing here. We do the insertion, and then we say, have we broken the heap condition? And so in this case, we have. And so we see that 42 is bigger than 11. So the parent is less than the child in this case. And so what we do when we have this problem is that we simply swap the two values. And so we can say that 42 and 11 swap. So 11 goes down there, 42 goes up there. Next thing we do is we now look at 42's new position and we compare it with the parent. And we say, well, is 42 less than the parent like it's supposed to be? No, it's not. So we've broken the heap condition. And so in this case, we can then do a second swap. And so 12 and 42 should now be swapped. Now that we've done that swap, we compare it to its new parent, and we see that 42 is less than its parent, so 42 is less than 100, and so in that case it's all right, and we're guaranteed that the heap condition now holds. And so if we look everywhere in the tree, we can see that the parent's always greater than the child. And so we managed to insert some new number, we did some swaps, up until the heap condition was intact again. And then at that point, we know that we have a binary heap and our number's been inserted correctly. Okay, so we've now inserted the number 42. Let's try and insert another number. So let's insert the number 45 now. So the first thing we do is we go to our complete binary tree and we say, where is the only place in the entire tree that we're actually allowed to do this insert? And that is going to be to the right of 11. So it's going to be the sibling of 11. So the right child of 12. So we're going to insert 45 over there. And then we simply need to say, does it conform to the heap condition? So we compare 45 and 12. We see no, that there's actually a problem, that 45 is bigger than 12, and so we make a swap. 12 goes down there, 45 goes up there. Next, we compare 45 with its new parent, and we say 45 and 42. Well, 45 is bigger, and so in that case, we see that we need to do a swap. So 42 moves down, 45 moves up. We then compare 45 with its parent, and we see that 100 is bigger than 45, and so we don't need to worry. The heap condition now holds, and we finished our insert correctly. So we see that in order to insert into a binary heap, it's a case of insert into the next open space, and then compare it with its parent, and if necessary, swap. Then compare with its new parent, and if necessary, swap, and compare with the new parent, and keep going until we get to a stage where we no longer need to perform a swap. Now, we can see that going from the bottom of the tree all the way to the top, if we just inserted the new biggest item, so let's have a look. If we insert the new biggest item, let's say 101. In this case, we then say, okay, well, where's the only place it can be inserted? And that will be to the left of 5. So 101 goes in there. We've now broken the heap condition, and so 101 and 5 need to swap. So 101 goes there. Whoops. 5 goes down there. We then compare 101 with its parent, and we see that there's a problem, and so we perform a swap. So 101 moves up, 45 moves down. We then compare it with its new parent. We see that there's a problem, and so we perform a swap. So 100 moves down, 101 moves up. We see that we've now gotten to the root of the tree, and so we know that, that we must have inserted a new biggest number. And so now that we're at the top of the tree, we can stop. We know that the biggest number is back at the root. Now in this case, we've seen that we went all the way from the bottom level, from a leaf, all the way up until we got to the root. So the number of swaps that we needed to do was going to say, well, how many nodes are there on this path all the way up to the top? And so we saw that there was going to be 1, 2, 3. 3 potential swaps. And so we see that that's also going to be the height of the tree. So the height of this tree is 1, 2, 3. And so in the worst case, we have to do h number of swaps. But luckily, because it's a complete binary tree, we know that h is bounded above by log n. So h is order log n. And so we know that even if it's the worst case and we have to do as many possible swaps as possible, we know that that number of swaps is still bounded above by some reasonable number. Okay, so let's say that we now have a tree, we have a binary heap, and we now want to remove the maximum element from the tree. So in this case, we always know that the maximum element is going to be at the root. And we said that that's a consequence of saying that the parent is always bigger than the child. So we know that the maximum number floats all the way up to the top. So it's just a case of saying, well, how can we remove this specific number from the tree? How do we remove the root from the tree? Now, we would have a problem if we simply wanted to delete the root, because now this is no longer a complete binary tree. We see that there's now a hole in it somewhere. So in order to avoid that, we rather need to say, well, what is the only number in this tree that we can actually delete? And so just like with inserting, we see that it's this number here on the very bottom. So when inserting, we said, well, where is the next open space? When deleting, we say, well, where was the last number inserted? And that's going to be this bottom one. So what we can do is we can simply swap the value of that bottom one up into the root. So 5 moves up there, and we can delete that node over there. We can remember that we need to return the value 101 at some point. Now that we've successfully deleted that node, we then need to check whether we've broken the heap condition. And so we can look at the root, we can look at 5, and we can see, well, we've replaced it with some smaller number. Has that broken the condition? And in this case, we see yes, it has. So 5 is less than 100, and it's less than 53. So we're going to swap 5 with one of its children, but we need to pick the child that fixes the heap property. So for example, if I tried to swap 5 and 53, we would see that there's still a problem because 53 is still less than 100. So we need to say, So we need to say, swap the node with its maximum child if that child is bigger than the value. So we're going to say, well, 5 is less than 100, and so in this case, we're going to swap them. Then we can say, compare 5 with its children. And we say, okay, 5 is less than the children, and so we've broken the heap condition, and so we swap it with its largest child. So in this case, we swap it with 45, and we get a tree that looks like that. We then compare 5 with its children, and in this case, it doesn't have any, so in that case, we're finished, and we know we're done. And now that we've done that, we know that we've restored the heap property, and we've successfully deleted an item from the tree. Now, in the absolute worst case, similar to what we've just done, the item that we moved to the top is a very small number. And so it means that it will have to swap all the way back until it gets to the bottom of the tree. So the worst case is when we have to do swaps that are of the order of the height of the tree again. Potentially we go from the root all the way down to the very bottom level. So again, we're saying that we potentially have to do h number of swaps, but we know that h is some reasonable number because it's bounded above by log n. And so we know that as the number of nodes increases in the tree, that the number of swaps that we potentially have to do in order to remove an item is still going to be quite reasonable. Okay, so let's do another example of a removal. So in this case, we now say, let's remove the next biggest number. So we can say, well, we know we're going to find that in the root. And so we know that it's going to be 100. So we need to remove this node, and we can't do that because it needs to stay a complete tree. So we go down to the only node that we can remove, which in this case is going to be 12. So we can say, well, remove 12 and put the value 12 up in the root. Now that we've done that, we've successfully deleted a node, so that's fine. And we then need to say, well, let's check whether we've broken the heap condition. So in this case we have, and we see that we have a 12 over there, a 45 and a 53. So we definitely need to swap it with one of its children. Now in this case, if we swapped with 45, 45 would still be less than 53, and so we'd have a problem. So we're going to swap with the biggest child, as always. And so 53 moves up to the top, and 12 moves down by one level. We then look at 12 and we say, okay, well, it's moved. So now we look at its new children. And okay, we see that 12 is less than 25. It's bigger than 6, but we've still broken the condition over here. So in this case, we then need to swap 12 and its largest child. So 25 moves up and 12 moves down. At this point, we've now reached the bottom of the tree, and so we're guaranteed that everything is fixed. We know that as soon as we don't need to make a swap, then the entire tree is fixed and we're finished. If we try and remove another item, so this time we'll be removing the next biggest item, which is 53. So we can remember 53, so we can return it later maybe. We then say, which node can we delete? Well, in this case, it's only going to be node 11. So we delete that node, and we copy its value into the root. So we overwrite the root. And then we simply say, well, compare 11 with its children. 11 is less than them, so we swap it with the largest child. So 45 moves up, 11 moves down. We then compare 11 with its children again. We see that it's less than 42, and so we perform the swap with the largest child. So 42 moves up, 11 moves down. We've now reached the bottom of the tree, and so we don't need to worry about it. We know that we're finished. The heap condition has now been restored, and this is now a valid binary heap. Okay, let's do one final example of removing. So given the same binary heap that we had before, let's remove the biggest item. So we see that that's 45. We replace it with the only node that we're allowed to delete. Now we see that we've run out of nodes on this bottom layer, which means that the next node is now number 6. It's this one over here. And so that's the only one we're allowed to remove. So we can remove the node with number 6 over there and move its value into the root. We then say, have we broken the heap condition? And so in this case we have. So we swap it with its largest child, which in this case is 42. So 6 moves down, 42 moves up. We then do one more check and we see that 6 is bigger than one of its children. And so we swap it with the larger of the two children. And so 6 and 11 swap. 6 moves down, 11 moves up. And now that we've reached the bottom, 6 has no children. And so we know that we're finished and we've restored the heap condition to the tree. Okay, so we've managed now to implement everything in our binary heap. We're able to add new items to the heap using push. And so to do that, we insert the number into the only possible open space that we have in the complete tree. And then we check whether we violated the heap condition and potentially swap it with its parents all the way up to the root. So in the best case, we don't have to do any swaps. In the worst case, we have to swap all the way up to the root. So the best case is when we possibly insert any number that's less than that parent that it gets, but we could specify and we could say a best case is when we insert a new minimum number into the tree, for example. And in that case, we're guaranteed to only do constant amount of work. But in the worst case, we insert the largest number, and that number has to be swapped all the way back up to the root. And so in that case, it takes order log n amount of time. And when we're popping an item, we always get the maximum value back from the tree. And so in that case, we swap with the only node that we're allowed to delete, so the node right at the very end of the complete tree. We swap it with that node, and then we potentially do swaps all the way back down to the bottom. In the best case, we don't have to do any swaps, but in the worst case, we have to swap all the way back down, which means we have to go again through the height of the tree. And so in the worst case, we're going to end up doing log n amount of time. Now that best case is very rarely ever going to happen, because if the number was at the bottom of the tree to start with, it means that probably, unless your tree is really very small, it's very unlikely that that node that we swapped up to the top will remain there. So you'll probably have to swap it most of the way down, if not all of the way down. So we can see that we can now do pushes and pops in log n time. And so compared to our other versions, before we had that it could take linear time and constant time, or constant time and linear time. So in this case, we see that we do quite a lot better than the linear time. And so if we were doing average case analysis, we would be able to say, how often do we do each of these different operations? And how long does it take us to do them? How long is it likely to take us in each case? And so we would have to look at the probability distribution of all the numbers that we're getting. But it turns out that on average, we do a lot better in the binary heap than we do in the sorted list. And the reason is that the binary heap doesn't actually keep the entire list sorted. It just keeps it partially sorted so that we know where the next biggest number is. And so because we have more relaxed constraints on our container of numbers, it means that we end up doing less work to enforce those constraints. Now let's suppose that we have some big list of numbers already, and these numbers are completely unordered and we'd like to build a binary heap out of them. So the one way to do this is to just create an empty binary heap and then insert all of the numbers one by one. And so if we know that the insertion takes us log n amount of time, and we can say that we're doing n insertions, then by repeatedly inserting, we're going to end up with something that takes some n log n amount of time. And then we can do that and build our entire binary heap, and that will work. But there is a better way to do this, and the algorithm to do this is quite an interesting one. So let's say that we have the numbers in our array, and let's say the numbers were 30, 12, 81, 64, 3, 100, 50. Right. So we can simply interpret this as a complete binary tree. And so if we draw it, we can see this 30, 12, 81, 64, 3, 100, 50. Right. So in this case, we can see that we've constructed our complete binary tree by just interpreting the numbers as a tree. And now what we can do is we can say, let's make small binary heaps first. So we're going to go through and say, well, for the leaves, we can simply consider them all binary heaps. So we don't really need to do anything fancy there. But then for this next layer going up, we can say, well, is the subtree rooted at 81, is that a binary heap? And so we look at it and we see, well, it is a complete binary tree, so we're fine with that. And it's not a binary heap because the heap condition is not obeyed, because 81 is less than 100. So we can simply do that swap. So we swap again with the maximum child, so 81 moves down and 100 moves up. And so that would be the same as swapping those numbers there. We can then move to the next subtree, rooted at that level, and we see that we've got 12. Is that a complete binary tree? No, it's not, because 12 is less than 64, and so we can simply perform the swap with the larger child. So 12 goes down, 64 moves up. We then go to the next level up, and so the next level up says we're looking at 30. Is this a binary heap? No, it's not, because 30 is less than both of its children, actually. So we swap it with the bigger of the two children, so we swap it with 100. So 100 moves up, 30 moves down. Now that we've moved 30 down, we potentially have broken this smaller binary heap over here. And so we need to say, okay, well, look at its children. Okay, there are children that are bigger, and so we do a swap with its maximum child. And so 81 moves up, 30 moves down. So we've now reached the bottom, or we've gotten to the point where we didn't need to do a swap. And so in that case, we know that this is now a binary heap. Now, it turns out that in the worst case, by following this algorithm, we do a linear amount of work. And so we can actually construct a binary heap a bit faster by simply saying, by simply looking at lots of small binary heaps first, and then adding them all together to make a bigger binary heap. So finally, the last thing I want to talk about is something called a heap sort. And a heap sort says, given some list of numbers, can we sort that list of numbers in an efficient way? And so we're going to look at we're going to look at a couple of different types of sorts between now and the end of the course. But this is just one of them. And so the one way to do this is to say, well, if we've got a binary heap, we can continually remove the top item from that heap, and we can do that in logarithmic time. And so if we do that n times, then we can get the maximum number, and then the next biggest number, and the next biggest number, and the next biggest number. And if we continually do that, we can build up a sorted list. And so we can say, well, given some list of n numbers, we first need to construct the heap. Now, we've just done an algorithm, and I've said that that takes a linear amount of time. So we do some linear amount of work to construct the heap, and then after that, we need to remove each of those numbers. So if we remove n numbers, and it takes us log n amount of work to remove a number, then we end up doing n log n amount of work to remove all the numbers. So overall, that means that the amount of work we do is going to be some linear function, an plus c, plus b, plus some n log n function, which we can simply say is going to be cn log n, possibly plus some constant term, some other constant term, but the one that we care about is this n log n. So over there, we can see that the entire thing works out to be an plus cn log n plus some extra constants that we might not care about. And so if we write this in big O notation, we can see that we're going to end up with some function that's n plus n log n. And if we have a look at those functions, if we actually plot the graph, we'll be able to see that n grows like that, and that n log n grows something like this. And so as n gets very, very large, we're essentially saying which of these two terms will dominate the function. And so as n gets very large, it's going to be the n log n that dominates. And so we know that this is going to be an n log n function. And so I recommend that you actually plot these out and have a look and see what the graphs do. Possibly even compare this to a quadratic function, so n squared, and see and make sure that you get comfortable with knowing which classes are better than others. And so we can now do a heap sort in n log n time by constructing a heap from the n numbers, which will take linear time, and then by continually removing a number from the heap. And that will give us all the numbers in descending order. If we wanted to get the numbers in ascending order, then we could simply work with a min heap. And a min heap says that the parent is always less than the children. Cool. So hopefully this covers everything that you need to know about heaps. This is just a quick review of the stuff that we spoke about properly in the lecture. So I hope this covers everything. And if you have any questions, feel free to ask.